Hello. Today we are going to learn convex schools in three dimensions. In previous lecture, we learned convex schools algorithms for 2D dimension, and all the definitions in our previous lecture will be correct for three dimensions. We just replace here uh, two replace 2 to 3 here and here, and we get correct definitions for three dimensions for convex schools in three-dimensional space. So in the previous lecture we learned algorithms how to find convex school for some points. In three dimensions we learned how to find it in three dimensions. Okay, here's demonstration how it looks like, and okay, so here's non-convex non-convex school. Here's convex school of the same points. Okay, so we are going to speak about vertices, and we are going to estimate complexity by using only vertices. So we can estimate it only by using vertices because the count of faces will be proportional to count of vertices. Here's a proof why is it true. So we consider if you consider edges, so it can be represented like this. So it will be odd count of count of vertices, and we can say it for faces too. So we can consider vertices, or we can consider vertices and estimate all complexity only for vertices. It will be the same if we consider faces or edges. Okay, so we are going to use come up some algorithms, generalize algorithms that we learn in 2D dimensions in 3D. So how to do it natively? So we consider every triplet of points, check if plane defined by it is extreme. If it is, we add it to the list of faces. So it will be the complexity will be On in On to the power of 4, because here we need to check. Here we need to perform On actions. So we learn gift wrapping into D dimension. Where is it? Gift wrapping. Jarvis wrapping. Here is this. Here it is. How it looks like into D dimension. We just sort all the points. Sort all the points by angle of some point. that we of the leftist point by leftist points, and then we choose the smallest the point with smallest angle again and again. We sort by this point, then we sort by this point, and so on. And you can understand that it will become the complexity will be 1 squared easily. So each time we need to choose minimum angle, minimum angle. So we need to do this in 3D dimension. How to do it? So let's consider once again Convex algorithm in 2D space. Here we need to choose point with smallest minimum with smallest x coordinate. Then we need to choose among all of them point with minimum y coordinate. Here we need to do it too. We choose point with minimum z coordinate. Then we need to choose between all of them point with minimum y coordinate, then with minimum x coordinate. Okay, then we get this point, and what we do next? We need to choose. Okay, here we need to choose. Как? If in 2D dimension we need to choose. We need to draw. We need to draw some line and compare on the angles of this line. Here we need to choose plane in 3 dimension. How we do it? How do we do it? Okay, we need to choose 3 points. We have already choose only one point. Choose only one point. Okay, second point. How to find second point? No, we can draw. We can place some plane that will be placed parallel to OX, OY coordinate, parallel to OX, Y plane. So it will be located like this. It will be located like this. Okay, then we need to choose the smallest angle between this point, between plane and all of this edge. All of this edge. How do you do it? Так, 1 second. I need to think. The easiest way to do it is to draw some face on this plane. On this plane, and then we need to compare angles between these two faces. I forgot what formula we need to use. We can support for every plane. We can support normal vector of it. Normal vector of all of these planes, of all of these faces. And then we need to compare vector that will be oriented outer our polygon and all of this and vectors and what? Sure. And vectors that not like this. We compare it a little bit later. We need to choose the smallest, the first edge, and we need to compare this vector and all of these vectors that uh, that located from this point. And that's it. Okay, we found the next edge. The next edge. Suppose it will be this edge, that have the smallest angle. Okay, then we need to found our first plane. Okay, we consider. It means we need to consider this normal vector that oriented from outer plane, and we can even consider all the vectors, all the I mean all the faces that based on this edge. It can be like this, it can be like this, or like this, and so on. And we need to choose the smallest of it. Okay, we choose the smallest of it, and finally we get the base of our induction, the base of our algorithm, the base plane, the first plane. The first phase. Okay, and we do the same algorithm that I considered, but we consider not this this normal vector. We consider first of all this vector, this normal vector that located outer of our polygon. Okay. So, how looks our induction? How does it look like? Um, First of all, you can notice that we get three edges that and all these edges correspond to two faces, this and this. So we need to we need to uh, we need to force from this edge, and this edge, and get next faces, and so on. We need to do the same algorithm that I already discussed. We need to found the smallest angle between this normal vector and all of these faces that located on, or that based on this edge, and so on. So we have some vectors and so on. Okay, here's the idea and how to implement it more easier. You need to support invariant. If you have some phase, normal vector of it is oriented to outside, to outer of our future polygon. Okay, we found we need to understand. You need to understand how to find how to define it if we have only one, or I mean, we need to define it if we consider the first phase. The first phase. Okay, you define it. You can get that your phase based on 3 points, but you need to choose between two classes of it, Uh, как это? How to on English? I forgot. Sorry. So I forgot how it's called English. On Russian it called правая ортонормированная тройка. You need to define it. Oh, by this rule. You need to define it by this rule. Okay. Okay. If you have 3 points, you can place it in other order, and you can get your neural vector located outer polygon or inner. Okay, and you need to choose it. You need to find out how to orient outer your face using this rule. Okay, here is so suppose we get some face on some step of our math induction. You can consider your math induction like this. You can use BFS to consider planes, to consider faces. So suppose you let's consider it. Suppose you get only one face, then you get three different faces, and so on. You need to place these faces to your stack or to your queue. You need to just do your math induction by BFS. Okay. We enumerate our math induction by layers of both BFS. I mean by layers of BFS like this. Okay, we consider some face. How to find? Let's look how to find. How to find the next. Okay, suppose you base your place on two vectors p1 and p2, p3, p1 and p3. Okay, how it looks like, how neat looks like to get it like this. p1, p2. So you need to get p1, p1, p2 vector, p1, p2, here is vector, and you need to multiply it by p1, p3, I think. P1, p3, let's check it. P1, p2, p1, p1, p2, p1, p3. That's correct. You can you can you can place your hand on display and check it like this rule, using this rule. Okay, we get normal vector. So we need to get normal vectors for those planes too that located outer of our polygon. Okay, so here is base edge p1, p2. We need to consider all of this. All of faces looks like this, and so on. So how to orient our vectors? Okay, if we consider this vector, p1, p2, and multiply it by p1, p6, let's check it, p1, p2, сейчас, p1, p2, так, p1, p2, no, you need to do like this, this vector, this is the first vector, this will be, the base vector will be the second, like this. Okay, and you multiply, and you get your scalar product by this, and you just get, if you multiply it by this, you get normal vectors like located outside, and what? And angle between all these vectors and your face and your normal vector and your base normal vector is smaller than p. And you don't need to check plane located. Sorry, just you don't need to check your plane located like this, like in this space or in this space, using this rule. So that's it. So you consider you place your all your faces that you get. So BFS, and you get Jarvis Convex school. And that's it. Okay, here is formal algorithm how to do it. I told you tricky part, how to do it in more easier way. And that's it. That's just Jarvis propping for 3D space. Okay, we have no Graham-Scal algorithm for 3D space. Let's consider the next. Let's consider divide and conquer algorithm that I didn't consider in 2D space, by the way. No, if you have some points, you need to find first of all, you need to find line that divide your space such that you have the same count of points. Then you do it recursively and get some разбиение сейчас. Then you get some split split. Okay. Next, you need to find convex hull for triangles and found a way how to merge it. For example, you have two triangles. You need to uh, find a way do how to find convex hull for triangles for two triangles. Then you no, then you recursively do the same thing. Let's consider two convex hulls, two random convex hulls that we need to merge. How you can do this? Um, as I as I remember correctly, you need to find line. You need to find the the upper and rightest point for left polygon, the upper point, the upper leftist point for right polygon. Then you need to connect it, and then you need to connect here too for uh, just for no, that's not true. That's not true. I forgot how to do it in 2D space. I think we need to check it to understand how to do it in 3D space. I considered four algorithms how to do it, but I didn't consider divide conquer algorithm. Divide conquer. Convex hull. Let's consider it. Oh, here it is. So you need to found this point and this point, but how to do it? How to do it? Um, okay, let's do some break. I need to learn how to do it. I don't sure that I told this algorithm correctly. In this set of points. Okay, let's continue. We need to uh, find upper and lower tangents to the right and left convex holes. Instead of finding upper left, upper down, and so on, upper right, and so on for all of the schools. So we found common schools with. We found edge with lowest tangents lowest and upper tangents of left and right hooks, and then we just we found point, and then we just provide some lines, and we need to delete all of these lines of this edge from our convex hull, and that's it. And this is just a step of our recursion. We we did the same recursion in algorithms like quicksort algorithm and what quicksort and no okay quicksort. We do the same thing in quicksort algorithm. We need to find a way how to split our points, and then we need to find and then we need to just consider the trivial step that looks like this. Okay. Okay, the same idea here in 3D space. We use the same idea as in 2D algorithm. We divide points into helpers P1 and P2, and then we recursively found convex hulls and merge it. Okay, instead O n squared algorithm in Jarvis warping, we get O n log n algorithm here. Okay, how it looks like? How does it look like? We okay, suppose in some step of consider some step of mountain action, we got some convex hulls. We need to merge it like this. So how do we do it? How do we do it? Start with the lower tangents, wrap around, find one face at a time. So we need to find the first face, that located with that have the smallest tangent, I think. Okay, next we do what? Next we need to use Jarvis warping algorithm. As I remember correctly. What? We need to find some edge that have smallest tangents, common tangent AB. Then we need to find face. We can consider all of the points, just all of the points that based on this vector, and do the same things that we did in Jarvis warping. We need to find the smallest angle. Now we need to find a triangle ABC. Thus AC is inch. No, да. That's it. Okay. We found our face. Then we need to do Jarvis warping. Jarvis warping. No, we just. Sorry. How can we do it? How can we found d fast instead of on? Now we need to find a triangle ABC. Thus AC is edge on the left hull or on the right hull. Okay. Now we have a new edge AC that's tangent repeat. Okay, but how can we do it in not only on O1 complexity, or not in O(n) complexity? Here's the deal. I don't know how to do it. Sorry. Now we have. So I don't know how to find the new point U in O1 complexity. Okay, we have some edge, then we do what? Then we need to find the smallest angle between all of these faces. How to do it? How to do it? Do you have some ideas? I don't have. In one complexity. Mm, maybe we. I come up. Maybe we need to consider. Нет. Ща. Maybe we need to consider what? Maybe we need to consider points that adjacent to this point. We have only 2 points here. Only 3 points. Нет. Only two points. Да. Only two points that located here and I think here. Okay. And we do it in and we can do it in one complexity because we have only 2 points, only 4 points as maximum. Do you agree with me? I think you agree with me. The hardest part, just we apply our induction, our supposement of our reduction here. As we found convex hull, we can consider only 2 points here. We need to consider only 2 points here. Okay? No, not all of them, because this is not this doesn't make any sense. Okay? And that's it. You don't need to, I think, to implement it. I just told you idea how to do it, and we do the same thing. We just consider adjacent points and drop our two convex hulls. Okay, then we got some convex hull. We need to delete points that located inside this convex hull, and that's it. You can think that we get complexity like O(n) squared. That's not true. If we consider all of this is convex hulls of our layer, recursion layer, suppose we can, here we have n1 points and so on, and so on. We have nk, for example, on some layer, and all of the sum is equal to n points. And we wrap on each step, we wrap two convex hulls only in O(n) of size of points complexity, and we get per layer we get O(n) complexity. So we have log n layers, and then that's why we get O(n) log n complexity. Hidden faces. Oh, here it is. How to do it? Use DFS or VFS. It's trivial, I think. Okay, that was quick. Hull. Oh, incremental 3D hull. No one. Let's consider it. I don't know. I didn't implement it, but let's consider. So we consider some point in 2D space. No, in 2D space we do it. We did it. We consider it. We just explain it in more detailed way. We consider some point that we need to add to our convex hull. So we contain our convex hull as two parts, upper and lower, and we define what part. Uh, First of all, we define to what part this point belongs to. Like uh, we just draw some line, and we can easily understand it. And then we just what we do. Sorry, так. We just using binary search we found we found first the first points that we need to delete. Um, then we just then we just provide some lines, or we just 1 second. No, we just draw we just consider two edges look like this. If we have here like that our two edges that our two edges represent inner angle, we delete this point. We delete this point from our convex hull, and so on, and so on, and so on. Okay, we need to do it the same thing in 3D space. In 3D space. Where does it? Where is it? It's complex topic. So I prepare so I consider presentation. Okay, P1. Here we have some convex hull. We already have it. We need to add new point. How can we do it? Point in front, behind, face. Okay, we need to define how we did it in the first algorithm. We need to define point in front or behind a face. Okay. Okay, we have some normal vectors. So we can just find angle between them. Yeah. Okay. Negative, positive. It's okay. Just 1 second. I need to learn it. I didn't think that we consider other convex hulls algorithms. You need to, in your homework, you need to implement Jarvis-Wropen algorithm for 3D or convex hull in 3D space. Так. I think we do the same thing. We do the same thing into this space. So we need to define the half space. Okay, and then we would what? I don't think I get the idea. We consider all the okay. We consider all of the planes, all the faces. We all of the spaces have normal vectors. Normal vectors that located outside of our that located outside of our polygon. Do you agree? Okay, and we just need to compare angle between them, and if this angle is what? Так. If this angle is... Я forgot. Тупой, острый. I forgot that words. If this angle is... Блин, стыдно. I forgot. Sorry. But I think you get the idea how to do it. Incrementally. In incremental way, we have, I think, an O(n) squared algorithm, O(n) algorithm to add new point. Да, yes. In incremental algorithm, we have O(n) squared algorithm. So we can do it. So we can, so that we just need to find a criteria how to delete this considered plane, or we just leave it. We just save it. Okay, maybe here. For each space, compute volume of tetra. Boy, VPI. Where's VPI? If volume less than null, f is visible. Так. Так, 1 second. F is visible. What does it mean? I think we can use this criteria, or criteria with normal vectors. But I didn't prove it. Yet. I haven't proved it yet. Compute volume of tetragon. VPI. What is VPI? For each face f of h. Okay. Face is some face of our polygon. I forgot to say, by the way, using Jefferson-Rotten algorithms that we consider, we don't get these places, these faces that looks like this. We get only faces that look like triangles. To delete, to get normal convex hull, we need to use 2D triangulation algorithm. But it's too complex. That it's just a theoretical mention. But yeah, I need to mention it. Where does it? No. Trip convex hulls. Where does it? Where is it? I forgot to say it. No, I have not. So we consider in the previous lecture we considered 2D triangulation, and we can use this algorithm to delete these edges. We consider one plane, and when we get convex hull, we just consider some planes that contain faces, and then we delete. We need to delete using 2D triangulation or 2D algorithm this edge. That's it. Okay, let's return to our algorithm. So consider the plane. I don't get the idea yet. I did. I haven't get ID yet. Got ID yet. Так, compute that volume of tetragon FPI. So we consider phase and PI. Okay. Ну да. Ага. Нет. Стоп, tetrahedron, it's not tetrahedron formed on 4 points. This picture is not correct, I think. Okay, we consider tetrahedron. So we consider like that all of our convex holes, our convex hole, contain only triangles, да? Сейчас, one second. Tetrahedron. Tetrahedron. Да. We consider tetrahedron. Tetrahedron, so our convex holes consider only triangles. So we consider some face, that is triangle, and some point. And why does it true? The volume is not null, I think. The volume is not null. What do they mean? If you consider this tetrahedron, we get that volume of it is not null. It's not zero, less than zero. We consider oriented volume, not just some volume. We just consider oriented volume, and that's why we get. And if we consider oriented volume, in some way we get positive volume, and the other way we get we get negative volume, like this. Okay, we need to consider, I think, but what we can do here? How can we get positive volume and negative? The first phase, and define its orientation. If no faces are visible, discard P. P must be inside H. Yes. Yes, find border edge of all visible faces. For each border edge is you construct a face API. I think if you implement this algorithm, you can easily understand it. How to do the step. How to find out criteria. let's consider again. So we get here, so each our polygon, each our triangle based on two vectors, and have normal vector. So I think they mean we need to consider volume that that is you need to consider this volume. So we consider point. When you consider point, it have two vectors. It have face that corresponded, and two vectors. And you need to consider volume, oriented volume that based on this vector and then these two vectors. The Сейчас. The hardest part of it is understand the order all of these vectors. The order will be look like this. You consider this vector. You place this vector to this production, and then you put two vectors to production in uh, in in order in just in what order? If you have AB vector and AB and this vector that locate that is the normal vector have you can represent it like this. You need to consider the next product. C vector, then A, and then B. And if it is negative, you need to delete it. You need to discard it from our convex hull. And that's it. Okay, and you do the same thing. Here's the algorithm of it. Formal algorithm. Pseudocode algorithm. Okay, that's it. Thank you for watching. If you have any questions, you can ask me to the chat.